Another way to find the relation among the view factors is from the fact that if you have surfaces, okay, and one of surface can include the surrounding surface too. As I mentioned a little bit earlier, these surfaces can be represented by the enclosure. Example, you have the surfaces combined as the enclosure. You probably has the surface 1 in the picture, surface 2, surface 3, and so on, including the surface I. Let's say that you have the end surface. So you know the temperature T1 of surface 1, T2, and surface 2. And you know the temperature of Ti, surface I, and the temperature of the surface N. And in this case, if you take a look at the surface I over here, okay? And the surface I itself emit the energy out, right? So in order to emit the energy out, there will be energy out from the surface 1, heat radiation from surface 1 to surface, from surface I to surface 1. It is the Qi to J. And they're going to be the heat radiation, this is I to surface 1. And it's going to be Q I to 2, and it's going to be Q I to 3, and so on. So if we sum it up, Q from surface I to 1, Qi surface I to 2, and including Q from surface I to I, and also surface I to N. If we sum all the heat up, there has to be, we call the summation of Q as Qi, meaning that it's going to be the Qi supplying the heat into this, right? This is the heat radiation balance at surface I. Okay? If we divide it by, and the Qi over here, it is the JIAI, right? And we divide the JIAI in odd term. By definition of view factor, you're going to have 1 equal to Fi1, Fi2, Fi3 to Fii, and also the Fin is going to be equal to 1. So in terms of summation, you can rewrite this relation just like that, okay? Summation of j equal to 1 to n of Fij going to be equal to 1. Okay, and it should be noted that Fii should be 0 if the surface I is flat or convex surface. Okay, and it's going to be if it's not, but sometimes it's not going to be 0 if the surface is concave. For example, something like this. This is surface I is concave. Then there might be possible that they're going to be the image radiosity coming out and arrive to itself. So in this case, Fi will not be 0, but for the flat plate or the convex surface. This one, in both cases, Fi going to be 0. Okay, understood? So this is the second relation that you have in addition to the first relation that you have. This two relation can allow you to use the relation instead of the table or the figure or the cross-string method. Okay. And so if you want to know how many view factor that you have to find it from the table, cross expression, or cross-string method, assuming that you have n surfaces. Okay, if you have n surfaces, the number of view factor to be calculated using expression or table or cross string method. It's supposed to be, you can find it as the n multiplied by n minus 1 over 2. I give you the example, okay? This is example where you have two surfaces. Surface 1, okay, and it radiate the heat out, and surface 2. This is surface 2, okay? Surface 2 facing up with the surface 1, and it's also have the radiation out too, okay? In this case, n equal to 2. So the number of view factor to be determined is 2 multiplied by 2 minus 1 over 2, which is equal to 1. So all you have to find the view factor, it's just only single value. And other than that, you can find it from the relation. In n equal to 2, for n equal to 2, you have to find F11, F12, F21, and F22. You don't have to find 4 of them from the table or cross-form expression or the cross-string method. Okay, so you need to find just only 1. That's fine. So in this case, intuition come. You don't even have to start by take a look at the table or closed form solution that we have, or even turning to the cross-string method now. You can, by intuition, because the surface 2 covering all the surface 1. So you know that all the radiation from surface 1 is going to go to surface 2 100%. See? The radiation from surface 1 is going to reach into the surface 2 100%. So by intuition, you're saying that F12 going to be equal to 1. Okay? So you know that. And then for the rest, you can use the relation. For example, you know that the F11 equal to 1. And you know that F11 plus F12 going to be equal to 1, 2. Okay? Oh, I'm sorry. F12 equal to 1. Okay? So when F12 equal to 1, F11 is going to be 0. Okay, and then if you know the F12 from reciprocity relation, you know that A12, I'm sorry, A1 F12 going to be equal to A2 F21. This is reciprocity relation. Remember from this equation. See? Okay. You substitute I with 1, you substitute J with 2. This is what you're going to have. So F21 going to be equal to A1 F12 and divided by A2. Okay. You just substitute A1, A2, and F12 because F12 equal to 1. So the relationship going to give you the F21. Okay. And then once you know the F21, F21 plus F22 going to be equal to 1. You substitute this into this and solve for the F22. Done. Okay, that's the example. Okay, let's move to the next slide. Well, sometime if you take a look at the, the, the table and you take a look at the closed form expression, you take a look at the cross-string method, you might not be able to find the figure that you have at hand. For example, if you take a look at the setup that you have, I will teach you, for example, just give you okay, here. Take a look at this problem first. The problem is that you need to find this is surface 1 and surface 4. Okay, surface 1 and surface 4. And you need to find F41. Okay? And you take a look, you try to use your intuition. Well, it's not going to work. So now it's your duty to take a look at the table. Okay. The closest that you have or the plot is this case. Okay. You take a look at the table. Okay, the closest one would be this. Okay. But the problem at hand that you have is this. It's not exactly in the table. If surface 4 and surface 1 are close to one another, F41 can be calculated from, I'm sorry, F41 can be found from the table or from the expression right away. Okay, but right now you have something like this. Table expression, you cannot have it. So how do you find F41 for this case? Well, we're gonna use the what's so-called view factor algebra. Okay. It is the case when we have the view factor from multiple surface. composite surface. Right? This is important. So, what is it? Let's take a look first. I will teach you what the composite surface is going to look like. And at the end, I will teach you how to apply what you learned from this to the problem that I previously showed you. Okay? Let's say we have the surface I. This is surface I. And then we have a surface J. Okay? And it seems that surface J can be decomposed to a number of small surfaces. Okay, surface J equal to surface 1 plus surface 2 and surface N. Okay, so if you represent this one, you can represent as the summation. You can write it down like that. Okay, so what happened? If you want to find the Fi to J, okay, you have to take a look at the radiosity. Radiosity kind of, if you want to find Fij, Fij is Q from I to J over, okay, and it's going to be Ji Ai, right? The concept is on the top, okay? So Q from I to J is going to decompose into Qi to J. Let me write it down here. Qi to J is going to be equal to Qi to area 1 plus Qi to area 2 plus Qi to area N, right? Q to area 1, Q to area 2, Q to area 3, and Q to area N, right? That. And then if you divide it by AI, Fij, right, on both sides. Okay, this is gonna have Fij. And this one is gonna be, oops, I'm sorry. It's gonna be Fi1, Fi2, Fi3 until Fin. So what happened, right? Okay, clean it up first. And then you can multiply AI on both sides. You're gonna get this and those terms. Okay, and then you use the reciprocity relation. What is it? It is the AI Fij equal to AJ Fji. And this is AI Fij, so I turn it to be AJ Fji. Do it the same on each term on the right hand side. AI Fi1 going to be A1 F1I. Do the same thing for the rest of the term. Okay. So we can even move AJ on the other side, and we write this equation in terms of the summation line. Okay. So what happened next? Well, the key element is on this equation. Let me clean it up. The key element is here. Okay, and then take a look if we can apply this to this question. Okay, so reminding you that we can find f Fij can be found for the case where we have this is surface I, surface J from either table or expression, right? Take a look. See, take a look here. Okay, I is over here, J is over here, fine. Okay, or this one, I is over here, J is over here. See, you can use this equation. You can use this graph. Okay, so what if I define the imaginary area, surface. I define the surface 2 as the combination of surface 3 and 4. This is surface 3, and this is in connection with surface 4. When you add surface 3 as surface 4, we define as surface 2, right? So we're going to use this equation. Okay, we write this equation from this situation. We will have A2 F21, okay, going to be equal to A3 F31 plus A4 F41. How is that? Because I use this equation, okay? And then I know that what I want is on this side. This is 4, so it should be F41. This is what I want. The red one is what I want, okay? Let's say we know A2, we know A3, we know A4. Given the dimension all you have from the picture itself, okay? How about A31 and A12? Because you can find this, okay, from either the table or expression. So these two can be found. So when we arrange the equation, F41 is going to be equal to A2 F21 minus A3 F31 over A4. Done. See? We make use of this equation. Here, this relation. Right now we have 3. See? In addition now to the second right here and the first right here. Reciprocating, summation of the view factor equal to 1, and also the view factor for composite surfaces. Okay. Now, giving you the more example. Okay. More example is to find the view factor F12 and F21. I will give you the case where you have two geometry for each surface. This is problem 1, problem 2, problem 3. But you need to find F12 and F21 in each of the problem. Let's start with the problem 1. Okay. For the surface 1 is the outer surface of the circle. Okay. And surface 2 is the inner surface of this rectangle. Okay, the diameter of the circle, it is the d, and the dimension of the rectangle is d, as I show you there. So right away, by intuition, if f12 equal to 1, why is that? Right, once again, f21, if f21 is q1 to 2 over a1 j1, right? Right. So this is the the definition of f12. Okay, and the all of the energy, the q1 going to be arrived to q2 for sure. So q12 going to be equal to the a1 j1. So it cancels to 1. Okay, by intuition, right? So you already got the f12. All you have to do is finding the f21 by reciprocating relation. A1 f12 going to be equal to a2 f21. So you rearrange this equation. This is what you're going to have, right? And then you can find the area of A1. Area of A1 is the pi d square, right? And the area of D2 is 6L squared multiplied by F12, it is 1. So, okay. Why is the area A2 is the 6L squared? Once again, if in the 3D, it is something like that, right? It's a cubic, and it has the circle or the sphere inside. Okay. And if you talk about the area of the sphere is going to be 4 pi r squared, right? Okay. And the inner side, the area of the cubic is going to be 6 because it has 6 faces multiplied by r squared. Okay. And r over here is equal to d over 2. Okay. So that's the first problem. Now, the second problem. The second problem is we talking about the area, this area, the enclosure, be something like that. Okay, so and you have 3 surfaces right now. Okay, and you have 3 surfaces. How many view factor that you have to find? Well, remember, getting back over here, n multiplied by n minus 1 over 2. Now, your n is 3. 3 multiplied by 3 minus 1 over 2. So this is 2, okay? 2 got cancelled, so you need 3, right? You need 3. you have to know three of them. Well, at first, you know that the F11 going to be equal to 0, right? Because the surface 1 is is flat, okay? And also F22 going to be 0, F33 going to be 0. See, you already know by intuition. You don't have to open the table, or you don't have to go for the expression. Okay, and after that, remember you need to find the F12 and F21. None of this telling the solution right away. However, if you take a look, you know the F11 plus F12 plus F13 equal to 1. Okay, and you know that this one equal to 0. So right now, you know right away F12 equal to F13. Okay. And you know it too because of the symmetry. Heat from here going to be divided to the A2 and A3. So by intuition, F13 is going to F12 going to be equal to F.5. Right? Because F12 equal to F13. This is going to give you F12 or F12. And you solve it, you're going to have F12 equal to 0.5. Okay? Now, you answer this, right? I cross this thing out. And after that, and once again, A12, F12 going to be equal to A21. I'm sorry. Yeah. A1, F12 going to be A2, F21. So you rewrite this equation, you're going to have A1 over A2, F12. Now you have the F12, just substitute, right? And you can find the A1 and A2, right? So this is going to have F21 equal to 0.71, okay? Okay, let's clean it up. And for the third one, you have a tank like that. And you have a lid on the top. You have the surface on the bottom of this tank. And A1, and if I draw the cross section like that. Okay. And you have three surfaces. Surface 1 is on the top. Surface 3 is on the bottom. And you have the inner surface, lateral surface. You call it surface 2. Okay? Now, you know right away that's F11 going to be 0 and F33 going to be 0 by your intuition. Okay? Then, if you take a look, you know that you have seen this one, right? This is I, this is J, you can find Fij, right? You've seen this somewhere. Let's take a look. Here we go. This is the case. Okay. This is the case. It is the case that you have the parallel disk sharing the coaxial parallel disk. Okay. You can find the Fij, and you can, and after that you can find the Fji also from the reciprocity relationship. But of course, if you have the geometry like this, you can read it from the table right away. Or if you don't like the table, you can use the equation like that. Okay, depends. What's your preference? And that's getting back to the problem at hand, right? So you can find the F13, and also the same thing gonna happen with F21, right? F31, same thing. So let's say you go to that table, do the graph, and you read it. Lead from the plot. It's equal to 0.17. Okay? Then you know right away, because this the F11 plus F12 plus F13 equal to 1. F11 equal to 0. F1 F13 equal to 0.17. You rewrite this equation, solving it, you're going to have the F12 equal to 0.83. And then you want to use the to use the reciprocity to find the F21. You can use it, okay? Substitute A1 and A2, you're going to get the F21 equal to 0.21. Okay, so practice this. Okay, there will be example inside the book, and also in the homework, and also in the problem set in at the end of this chapter. We'll find all the problems set that you can practice. Right? Now, at this point, okay, I will make a summary. Summary is that you can find the Q, the radiation out of the surface I to surface J. How do you find it? You have to know AI, JI, okay, multiplied by Fij. Okay, and how do you find the Fij again? Fij over here, you can find it from the table of expression. You can find it the plot, or you can find it from the Krusner method. You can find it from the reciprocity relationship. You can find of sum of the view factor equal to 1. And from the, view factor of the composite surfaces. Okay? By having this is 1, 2, 3. What is 1, 2, 3 again? Here. This is number 3. Here. This is number 2. Let me clean it up first so you can take a look clearly. This is number 2, right? And let me clean it up here. And this is number 1. Okay, so this is summary. Fij can be found from 1, 2, 3, 4, 5, 6 possible way. Okay, so let me remind you that up to this point, I haven't say anything about how to find. Let's take a look. Ji. I haven't talked about it yet. Okay, but later on, I will show you how to solve for it. Okay, but right now you learn how to find the Fij in order to find the Qi to J. Heat radiation from surface I to surface J. Okay. Well, when you have two surfaces, for example, like this surface and that surface, okay, you're gonna have the radiation. This is I, this is J, Qi to J. And then on the opposite, you're gonna have Qj to I, meaning that this is I losing energy. This is I gaining energy, right? If your surface of interest is surface I, you're gonna have radiosity leaving away, taking some energy out from the surface I, that's losing energy. But in the same time, the surface J gonna bring energy into the surface I. Okay, that's Qj back to I. How do you find the resulting energy, if it is gaining energy or is losing energy? We talked about radiation exchange. Okay, so for example, in this case, we're going to define the new term. New term would be Qij. Okay, this is radiation exchange. What is the radiation exchange again? It is equal to Qi to J minus Qj back to I. Okay. Okay, this is what's so-called radiation exchange. And at the beginning, we will talk about the radiation exchange in the case where surface 1 and surface 2, or surface I and surface J, they are all black surface. Black, black. Okay, how you do? Well, in case of the black surface, you have to take a look at the equation first. This is the equation that we have been talking about. How do you get this one? Because we know that Fij by definition is Qi to J over Ai Ji. Right? Okay, and just rearrange the equation, you can find Qi to J. The thing is that when you take the radiosity J, what is the radiosity again? Radiosity is the emission plus reflection. Right? So This is the concept of radiosity. For the black body, you don't have a reflection. In black body, we can say no reflection. When black body have no reflection, you're gonna have J equal to emission. So Ji equal to Ei. Remember, and if for the black body, Ei over here is gonna be T sigma Ti to the fourth. Okay, and sometime for the black body, we can call Ei as EBI, right? So this one is EBI. So Ji equal to EBI. Understood? Let me clean it up. Okay. So this equation can be written into this form. AIFij multiplied by EBI. I just switching the order of J and F. Okay. And J equal to EBI. Similarly, you can find starting from Q, from J to I, we're just switching I to Bj and switching J to Bi. This is what you have. Okay. By definition of Qij, radiation exchange equal to radiation exchange Qij equal to Qi to J minus Qj to I. Just plug this thing in here, plug this thing in here. Okay. And this is what you can have. So after plugging in, you get something like this, and rearrange this term again, you're gonna get something like that. Okay, so now, how about we're not gonna talk just only two surfaces. We're gonna talk about the enclosure, and let's say enclosure have n surfaces. Okay, and so if you talk about the surface I, and this is surface 1, surface 2, surface 3, surface 4, surface 5, for example. Surface 1, right? This is surface, let's say, surface I. And this is surface 1, 2, 3, right? So you're going to have radiation exchange QI1, and then you're going to have QI2, you're going to have a QI3, you're going to have a QI4. Okay? So if you have n surfaces, you're going to end up with have the n QIN. Okay? So for the surface I, it's going to have a number of exchanges, namely QI1, QI2 to QIN. Okay? Each of radiation, it can be positive or negative. Let's take a look. What is the positive and negative mean? Okay? If QIJ is the positive sign, okay, this is losing energy. Lost energy. This is gain energy. Okay? Because this is the radiosity out. This is radiation in. When it is positive, when it is the positive, meaning the surface losing energy. And if it is negative, meaning surface gaining energy. Okay, got that? Okay. So, but if the enclosure is in steady state or in equilibrium, okay, the surface eye cannot losing energy or gaining the energy to get the steady state. No way. It's impossible. If it's losing energy, the surface cannot keep the temperature constant. On the other way around, if it's gaining energy, the temperature tend to go up. You have to, you know, release the energy that it gains at some point in order to bring the temperature down to get the steady state or in equilibrium. So if you allow me to this thing up, okay, you have a surface like that, then you have, this is surface I, you have QI1, you have QI2, you have QI3, and so on to QIN, right? And each of them can be positive or negative. And when they sum it up, you're gonna have it can be a negative sign and it can be positive sign. Either negative or positive. The situation of steady state cannot happen unless you need QI to supply. Okay, that's why we're gonna call it that QI is gonna be equal to Q radiation exchange from I to 1, radiation exchange from I to 2, until QI to the surface N, providing that the enclosure have N surfaces. Okay, so in that case, I will write the equation 1 again. Write that, okay? QI equal to QI1 plus QI2, and so on until the QIN. Okay. And how will you find each in the term? Well, you just saw it. See, this thing for the black body. Okay, you just substitute J with 1, substitute J with 2, substitute J with 3, and you're gonna have all this term. Okay, up into the surface one. So for the radiation balance, okay, you're gonna have QI equal to this in terms of summation. Okay, and I listed over here, if QI is positive, it means that heat has to be supplied to the surface eye. Otherwise, it's gonna losing energy. Okay, and you cannot maintain the temperature of the surface eye. If QI is negative, meaning that the surface eye gaining energy, you have to take the heat out from the surface eye. Okay, understand this. What the QI gonna look like, or QI, what it meant by saying it this QI. So don't be confused. They're gonna be QI, QIJ, and QI2J. Different meaning. Okay, this is radiation radiosity from surface I reaching for the surface J. And this one equal to QI to J minus QJ to I is the radiation exchange. Okay, and QI over here is this equation. It is the heat that has to supply or taken away from the surface I. Okay, so give you an example, more example. How about I have 3 surfaces? How so? This is 3 surfaces. Surface 2, surface 1, and surface 3. 2, 1, 3. Okay? And then you use this, the you use this equation and write it down. Okay, and you know that f11 gonna be equal to 0. So instead of having three terms on the right hand side, it's gonna be just only 2 terms. Okay, and then Q1 gonna be equal to sigma T1 to the fourth minus T2 to the fourth over I bring the A1 F12 on the bottom of the ratio. Okay, I do the same for the second term. Okay, and this is, oh, I missed this one. It's going to be, should be a 1, 2, 1, 3. I'm sorry. Should be, make the correction 1, 3. Okay, so this is, if you take a look, this is the Q1. Okay, in, and you have the on two sides, this Q1, 2, and this is Q1, 3, right? So this is basically, it's just the radiation balance, right? Okay, and you do the same for Q2. Q2 going here is going to be Q21, and this is going to be Q23, and you got this equation. And you do the same. It is the this is Q3, and this is Q31, and this is this is QT2, this is Q31. Okay, and you get this equation. So take a look at this. You have a system, okay, of 3 equations. Each equation seems like the nodal analysis. You remember in the class of the electrical engineering, you have nodal analysis like that, and you can see that. Okay, this is the like the circuit analogy once again. It seems that for the black body, let me clean it up. For the black body, you can represent the black body by the nodal, like that. A node, the point. And the you have a potential of the node as the EB1. Potential here is the EB2, and the potential here is the EB3. Okay, and it seems that between the surface 1 and surface 2, there is the resistance. What is the resistance again? Is 1A1F12. Okay, and resistance over here is going to be 1 over A1F13. Okay, and the nodal analysis is going to be, this is Q1 going in. Q1 is going to EB1. I'm going to use the blue one, B1. Okay, nodal analysis from here, EB1 minus EB2 on this. Okay, it's across the resistance, which is 1 over A1F12. Okay, and how about on this side? On this side is across the EB1 minus EB3, right? Because this is the across the potential like that over the resistance. Resistance would be 1 A1 F13. So you can write the equation in terms of nodal analysis too, right? And if you do, okay, if you do the nodal analysis on the surface 2, how about nodal analysis on surface 2? Okay, from here, Q2. Q2, when you have a Q2 going in, it's going to spreading into two parts, which is the Q2 back to 3 and Q2 back to 1. So basically, Q2 going to be equal to Q21 plus Q23, right? So what is the Q2? Q2 is going to be equal to, because it's across this resistance. So let me make it blue, okay? Across this resistance. What is this resistance again? It's equal to 1 over A1, A2, F21, which it's happened that 1 over A2, F21 going to be equal to 1 over A1, F12, right? Because of what? Because of the reciprocity relationship. Okay, so across the 2 and 1, you're going to have EB2 minus EB1 over 1 over A2 F21. Do the same for EB2 minus EB3. It's going to be over 1 over A2 F23. Okay, so you're going to have yourself the second equation. If you think of it as a circuit analogy. Okay, it's a circuit analogy. That's why, you know, we have the graphic representation, and you will see that we have the thermal resistance, radiation resistance once again. Okay, so let me clean it up first. What you learn? Summary. Okay, potential of the black surface is EB. For example, here is CB2, here is CB1, and this is AB3. Remember, EB is the sigma T to the 4. So EB1 is going to be equal to sigma T1 to the 4. EB2 going to be sigma T2 to the 4. EB3 going to be equal to sigma E3 to the 4. That's for example. Okay? And the next, radiation resistance between two surfaces. For example, I and J is going to be equal to AI Fij, or it can be equal to AJ Fji. Doesn't matter because these two are equal anyway by reciprocity reciprocity relation. Okay, and this is the summary, the first one, and the resistance, second one, the third. Okay, circuit analogy applied. Okay. Now you can see that even though you see the circuit analogy in terms of the conduction, and we already tested you the circuit analogy in the midterm exam already, but it's not over yet. Circuit analogy is still applying to radiation also, and you have to learn thermal radiation resistance And now you know the radiation resistance between the two surfaces can be written in terms of 1 over AI Fij, if it's a resistance between the surface I and the surface J. Okay?